All right, so you know how our brains can recognize, like, the number 3 no matter how it's drawn, right?
Yeah, like loopy, slanted, or even just a few pixels on a screen. We just know it's a 3.
But, like, imagine having to tell a computer how to do that.
Especially when all it sees is, that grid of tiny squares, some light, some dark.
Right. It's, like, super easy for us, but, like, crazy hard for a computer.
For a computer, that's a ton of data to make sense of.
Yeah. And that's basically the whole point of neural network.
They're everywhere now, right? Like powering recommendations, helping doctors, translating languages.
Exactly. I mean, they're like this fundamental AI tool now.
Yeah, and even though the math behind them can get, kind of complicated,
Yeah.
the basic idea is actually pretty elegant.
Yeah, it really is. So you and I, for this deep dive, we're going to take apart one of these neural networks.
Okay, sounds good.
Our mission is to, like, really understand from the bottom up how a basic network can recognize handwritten digits.
Like those numbers 0 through 9 from a 28 by 28 pixel image.
Yep, exactly that. And we're going to do it, like, assuming that, the listener isn't a computer scientist.
Right. Start simple.
Exactly, from the ground up. And we're focusing on what's called, like, the vanilla feed-forward neural network.
The OG recipe, so to speak.
Yeah, exactly. The feed-forward just means that, like, information flows one way. So from input to output.
No looping back.
Right, exactly. No loops. And even with this, like, basic design, it can still learn to recognize digits.
Which is, yeah, pretty amazing when you think about it. It's like, how can a bunch of simple parts do something that feels so smart?
It really is. And just to be clear, this is, like, part 1 of 2.
Okay.
So today we're focused on, like, the structure, what the network is.
The anatomy.
Exactly, yeah. And then in our next deep dive, we'll talk about how the network actually learns.
How it figures things out.
Exactly, so make sure to come back for that.
Yeah.
And I think it's really cool that these artificial networks, like, they're actually inspired by our own nervous system.
Right, the human brain is the original neural network.
Exactly, yeah. And so we'll see some interesting connections as we go along today. All right, so let's start with the most basic element,
Okay.
the neuron.
Okay, the neuron.
And when we say neuron here, we're not talking about, like, the biological ones in your brain.
Not yet, anyway.
Yeah. Instead, think of it like a container that holds just a single number.
Okay.
And this number is always between 0 and 1.
Okay.
And we call this the neuron's activation. So basically, it's like how on that neuron is.
So the higher the number, the more active the neuron is.
Exactly, yeah.
Okay, I get it.
So let's connect this back to that input image.
Okay.
Remember, the first layer of our network has 784 neurons, right?
28 by 28, that's the size of our image.
Exactly. So each of these neurons in the first layer, it's representing 1 pixel in the image.
Gotcha.
And its activation, remember the number between 0 and 1 that shows the grayscale value of that pixel.
So like 0 for black, 1 for white.
Exactly. And, like, values in between for all the shades of gray. So you can kind of think of this first layer almost like a digital snapshot of the image.
Like a grid of tiny lights where each light's brightness shows how dark or light that pixel is.
I like that.
Yeah.
That's a really good way to think about it. Okay, so then at the very end of our network, we have the output layer.
Okay.
Now, this layer only has 10 neurons,
Okay.
and each one represents one of the digits that we want to recognize.
So 0, 1, 2, all the way to 9.
Exactly. And so the activation of each of these neurons tells us how confident the network is that the input image is that specific digit.
Okay, so if the neuron representing, say, the number 3 has a high activation, the network's saying, hey, I think this is a 3.
Exactly. Exactly. And then all the stuff between the input and the output, that's where the hidden layers come in.
Ah, the hidden layers, the mystery zone.
Yeah. And that's where the network really starts to, like, learn and understand the image.
Okay.
So for our example today, we're going to use 2 hidden layers. Okay.
And we're going to say each of them has 16 neurons.
16. Okay.
Now, you might be wondering, like, why 2 layers? Why 16 neurons?
Yeah. Why those numbers?
So 2 layers, it just helps show how the network processes information in steps. Right?
Okay.
Makes it a little easier to understand. And 16 is just like, a manageable number to think about.
Right.
Because in real-world networks, these numbers can be way bigger.
Oh, yeah, for sure. And a lot of times it comes down to experimentation, right?
Yeah, exactly. Trial and error. They're like, oh, yeah, let's try this, let's try that. But the important part is what's happening in these layers. They're figuring out how to represent the input image in more and more abstract ways.
So like maybe the first hidden layer is looking for little edges or curves, right?
Mm-hmm.
And then the next one takes those and combines them into bigger shapes.
Yeah, like pieces of a digit.
Right, like a loop for a 6 or a straight line for a 1.
Exactly. So we have this flow of activation,
Okay.
like how on each neuron is. And that flows from one layer to the next. Makes sense.
And like the onness of a neuron in one layer, it influences the onness of neurons in the next layer.
It's like a chain reaction.
Yeah, exactly.
Yeah.
And how these influences are calculated, that's like the heart of how the network works.
It's how the network takes those simple inputs and turns them into something meaningful.
Right, it's like the secret sauce. Okay, so how do these layers actually like connect to each other?
Okay, how do they connect?
Well, I remember we talked about the brain analogy. Like in our brains, neurons fire and they can trigger other neurons to fire, right?
Yeah.
So in our artificial network, each connection between a neuron in one layer
Uh-huh.
and a neuron in the next layer, it has what we call a weight.
Okay, oh, wait.
And a weight is basically, think of it like a volume knob for each connection.
Okay.
So it determines how much influence the activation of one neuron has on the neuron it's connected to.
So a high weight means a strong connection?
Yeah, exactly. It's like turning up the volume.
Okay.
And a weight, it's just a number. It could be positive or negative.
So a positive weight means that one neuron kind of encourages the next one to be more active.
Yeah.
And a negative weight kind of discourages it.
Exactly, yeah. So now let's think about just one neuron in our second layer,
Okay.
which is the first hidden layer.
Right.
And its activation is going to depend on the activations of all 784 neurons in the first layer.
Wow, so it's getting input from every single pixel.
It is, it is. So for each connection, we multiply the first layer neuron's activation by its weight.
Okay.
And then we add up all of those multiplied values, and we call that the weighted sum.
Yeah.
It's like we're taking all the inputs, and we're either amplifying them or reducing them based on those weights.
Kind of like a mixing board where
Yeah.
each input has its own volume control.
Yeah, that's a really good analogy. Now, it can be really useful to like actually visualize these weights.
Okay.
Imagine we take the weights connected to that one neuron in the second layer, and we lay them out as a 28 by 28 grid, just like the image. And then we color them. So like if a weight is positive, we color it green.
Okay. Green for positive,
And if it's negative, we color it red.
red for negative. Okay.
And then the brighter the color, the stronger the weight. So now if most of the weights are close to 0, and there's like a small bright green patch somewhere in the grid,
What would that mean?
well, that second layer neuron, it would mostly be responding to activity in that specific part of the original image.
Oh, so it's like it's focusing its attention on that area.
Yeah, exactly. It's looking for something in that location.
Yeah.
Now, what if we have positive weights in a small area, but surrounded by negative weights?
That's interesting.
Yeah, what do you think that would do?
Well, maybe that neuron would be good at detecting edges.
Yes, exactly.
Because it would respond strongly to the light part, but not if the surrounding area was also light.
Right, so it's really sensitive to that contrast between light and dark, which is what an edge is.
Cool. So it's like by setting the weights, we can make the neuron look for specific features.
Exactly. Now, there's one more piece to how we calculate a neuron's activation.
Okay.
And that's the bias.
The bias. Okay.
Now, the bias is just a single number,
Okay.
and it's added to that weighted sum that we were just talking about.
Okay.
Think of it like a baseline level of activation that a neuron needs to overcome to turn on.
So a negative bias makes it harder to activate.
Yeah, the weighted sum has to be really positive to overcome it.
And a positive bias makes it easier.
Yeah, exactly. It's like each neuron has its own personal threshold for how much input it needs. So, just to recap, for a neuron in our second layer, it has 784 weights, one for each connection from the first layer, and it has one bias. And all those weights and the bias, they control how much input that neuron gets from the previous layer.
Okay. And then the same thing happens for every neuron in all the other layers.
Yeah, exactly. Each neuron sums up all the inputs it's getting for the previous layer, taking into account the weights and the bias.
Right.
So now we've got this weighted sum plus the bias. But remember, our neuron activations, they need to be between 0 and 1.
Right. Between 0 and 1.
And that weighted sum plus the bias, it could be anything, like any number.
Right. It could be huge, could be tiny, it could even be negative.
Exactly. So we need a way to squash that number down to that 0 to 1 range.
Okay.
And we use something called an activation function to do that.
Activation function, I see.
Yeah, and this is really important because this is what makes the network nonlinear.
So without it, the whole network would basically be like a single layer.
Exactly, and that would really limit what it could learn.
Makes sense?
So a very common activation function, especially like back in the day, was the sigmoid function.
Sigmoid, okay.
And it's got this really characteristic S shape. It takes any number you throw at it and spits out a number between 0 and 1. So like really negative numbers get squashed down close to 0.
Okay.
And really big positive numbers that get squashed up close to 1.
Okay.
And in the middle, it's like a nice smooth curve.
Yeah.
So the sigmoid function, it's like this gatekeeper that's making sure the activation of every neuron stays within that 0 to 1 range.
It's taking the raw input, the weighted sum plus bias, and transforming it into something that makes sense as an activation.
Exactly. So to put it all together, the activation of a neuron in the second layer,
Yeah.
it basically comes down to how positive its weighted input is, after adding the bias. And then we squash it down to between 0 and 1 using that sigmoid function.
Okay, that makes sense. And then that activation becomes the input for the next layer, right?
Yeah, and the whole process just repeats itself like all the way through the
The whole
network.
thing keeps flowing forward.
Exactly.
Yep.
Okay, so let's step back for a second and look at the whole system.
Okay.
We've got those 784 input neurons, then a hidden layer with 16, another hidden layer with 16, and then our output layer with 10.
Right.
So think about all those weights and biases.
Okay.
All those little knobs that control how the network behaves. Between the input layer and the first hidden layer, we've got 784 inputs connected to 16 neurons. So that's 784 times 16 weights plus 16 biases.
Okay, a lot of weights.
Yeah, and then between the hidden layers, it's 16 neurons connected to 16, so another 16 times 16 weights plus 16 biases.
Okay.
And then finally, from the second hidden layer to the output layer, it's 16 times 10 weights plus 10 biases.
Okay.
And so if we add all of that up, we end up with somewhere around 13,000 weights and biases.
Wow, that's a lot of knobs to adjust.
It is. That's like more adjustable knobs than you'd find on a spaceship or something.
And that's just for the simple network, right? Imagine a network with hundreds of layers and millions of neurons.
Yeah, exactly. It gets really crazy. And so this brings us to training.
Yeah.
When we say we're training a neural network,
Yeah.
what we're talking about is finding the best possible values for all those thousands of weights and biases.
So the network can actually do what we want it to do.
Exactly, like recognize a handwritten digit.
And it has to learn all of that just by looking at examples, right?
Yeah, isn't that crazy? And it's really interesting to think about what each layer might be learning.
Yeah, like what's going on in those hidden layers.
Now, maybe those 16 neurons in the first hidden layer, they're learning to find really simple patterns.
Like little lines or curves.
Yeah, exactly. And then those neurons in the second hidden layer, maybe they're taking those simple features and combining them into like bigger shapes.
Like parts of a digit.
Right, like a loop or a straight line. And then finally, the output layer is looking at all those shapes and saying, okay, based on this combination, I think this is a 7.
It's learning to recognize more and more complex features as you go deeper into the network.
Exactly. It's like building up an understanding in steps.
And even though we can't really know exactly what each neuron is doing,
Yeah.
it's still helpful to think about it this way, right? Like it's learning a hierarchy of features.
Yeah, and it makes sense if you think about how we recognize things, right? Like
Yeah.
to recognize a complex shape, like the curve in an 8 or a 9,
Yeah.
you can break it down into those little pieces.
The changes in direction that make up the curve.
Exactly, and it seems like that's kind of what the network's doing too. And this whole idea of like recognizing patterns,
Yeah.
it goes way beyond just handwritten digits, right?
Oh, yeah, absolutely.
Like think about medical images.
Right. Doctors could use this to help diagnose diseases.
Yeah. Or self-driving cars.
They need to be able to see pedestrians and other cars.
Exactly. And it's not just limited to images either.
Yeah, that's true.
Like think about speech recognition.
Okay, yeah.
You start with those raw sound waves, and then you're picking out individual sounds,
Uh-huh.
and then those get combined into words and then sentences. It seems like maybe there's a similar like layered analysis happening there too.
Yeah, it's all about recognizing patterns in data, no matter what kind of data it is.
Exactly, yeah. Now, for those of you who enjoy a bit of math, there's a really elegant way to write down all these calculations.
Okay, using vectors and matrices.
Yep, exactly. So remember how each neuron in a layer has an activation?
Yeah.
We can take all those activations and put them into a vertical list,
Okay.
and that's called a vector.
A vector. Okay.
And so then all the weights that connect one layer to the next, they can be organized into a matrix,
Okay, a matrix.
which is just a grid of numbers.
Okay.
And each row in that matrix represents the connections going to a specific neuron in the next layer.
Okay.
So to calculate the weighted sum for like all the neurons in a layer at the same time,
Yeah.
we use matrix vector multiplication.
So you're multiplying that weight matrix by the activation vector of the previous layer.
Yeah, exactly. And it lets you do all those calculations at the same time.
Makes it a lot faster than doing each one individually.
Yeah, much more efficient. And what about the biases?
Yeah, what about the biases?
Well, we put those into a vector too,
Okay.
and then we just add that to the result of the matrix vector multiplication. And then finally, we apply our activation function, like the sigmoid, to each number in that resulting vector.
And that gives us the activations for the next layer.
Exactly. So this math doesn't just look neat. It also explains why we use those special libraries that are optimized for matrix operations to run these networks.
Yeah, because matrix operations are really at the heart of how these networks do their calculations.
Yeah, exactly. So basically, at its core, each neuron is like its own little function.
Okay.
It takes the activations from the previous layer as input,
Right.
performs that weighted sum, adds the bias, and then spits out a number between 0 and 1.
It's activation.
Yeah, and the whole network is just this giant complex function that takes in 784 numbers.
The pixel values.
Yeah, and gives you 10 numbers as output.
The confidence scores for each digit.
Exactly. And it's probably a good thing it's so complex, right?
Yeah.
Yeah.
I mean, if it was too simple, it probably couldn't learn to recognize all those different ways people write digits.
Yeah, that's true. It needs that complexity to capture all the patterns in the data. So now this leads us to the big question.
The big question.
How does this network actually learn?
Yeah, how does it figure out the right values for all those weights and biases?
Just by looking at lots of examples.
Right. How does it go from knowing nothing to being able to tell a 2 from a 5?
It's a little bit magical.
It is, and the answer lies in things like loss functions and gradient descent and backpropagation, which is how the network actually learns from its mistakes.
Exactly. And that's exactly what we're going to be diving into in our next deep dive. So make sure you stick around for that.
Yeah, it's going to be a good one.
Oh, before we wrap up this part, I just remember something interesting we were talking about earlier. Remember the sigmoid function?
Yeah, the S-shaped one.
So Leisha Lai, she's a researcher in this area, pointed out that the sigmoid, it was really popular in those early neural networks.
Right, because it kept the neuron outputs between 0 and 1, which was kind of inspired by how real neurons in the brain work.
Yeah, like they're either on or off.
Yeah, exactly. But she also mentioned that the sigmoid, it's not as common now.
Oh, really?
Yeah, because in a lot of modern networks, it turns out training can be much faster and more effective using other activation functions.
Oh, interesting. So, like, what else is there?
One popular one is called ReLU.
ReLU, okay.
It stands for Rectified Linear Unit,
Okay,
but the math behind it is super simple.
okay.
So if you give it a number like, let's say, x, ReLU just gives you back the bigger of 0 and x.
Okay.
So if x is positive, you get x. If x is negative, you get 0.
So it's like it only turns on if the input is positive.
Exactly. Kind of like how a real neuron needs enough input to reach its firing threshold.
I see.
And researchers have found that using ReLU often makes training those deep networks a lot better than using sigmoid.
Wow, that's fascinating. It's like even these little details can make a big difference in how well the network learns.
Exactly. It shows how much research and fine-tuning goes into designing these systems.
Okay, so let's do a quick recap of what we've covered in this first part. We talked about how neural networks, for recognizing digits, they're organized in layers.
Right, with connections between the neurons in each layer.
Uh-huh. And each connection has a weight, and each neuron also has a bias. And then activations flow from one layer to the next.
Based on a weighted sum of the inputs and transformed by an activation function?
Yeah, like the sigmoid or ReLU.
Yeah.
And we also saw that even a simple network can have thousands of adjustable parameters, those weights and biases.
And those are what allow the network to learn and make accurate predictions.
Right. And so in our next deep dive, we're going to answer the question, how does the network actually learn the best values for all those weights and biases?
We'll explore how it trains on data and gets better at recognizing digits.
Exactly. So make sure you come back for that. It's going to be really interesting.
And before we go, here's something to think about. This whole idea of breaking down a complex task into a hierarchy of simpler features, it might be a fundamental principle not just for AI, but for how our own brains work, too.
That's interesting.
Yeah, like maybe other complex problems in all sorts of different fields, they could be solved by figuring out those intermediate levels of abstraction.
That's a really cool idea, something to ponder for sure. Thanks for listening, everyone.
And we'll see you in the next deep dive.